Okay, so today we have a few classes left now. So what we are going to do is to talk about a couple of applications of what we have been doing in all this semester. One is phase diagrams. We'll continue talking about that. And the other is we'll talk a little bit about chemical equilibrium. Those are the two things. So phase diagrams, we talked a bit. Let's talk a little bit more and try to construct a simple phase diagram of a two-component fully mixable system with two phases. And these two phases could be solid liquid. These two phases could be anything. I will assume they are called liquid and vapor, okay? So I'll give you the basic idea, and I like this phase diagram a lot because if you understand what's going on here, then effectively you get ready for this and one more phase diagram that we will do on Thursday and probably next week. Then you're ready for like as complicated as a phase diagram as you can face. You know, you're ready. It's the same simple idea that applies. So what do I mean? By the way, notice the word mixable. It's not M-I-X-I-B-L-E. Apparently, it's written as M-I-S-C-I-B-L-E. It's peculiarities of the language English, and don't blame me. So what this means is so let's jog your memory about the regular solution model, okay? In regular solution model, what was the final expression that we had? Our final expression was that delta mixing G is equal to omega XA XB plus RT XA ln XA plus XB ln XB. And in this one, if we had two types of behavior, right? We had omega less than 0 or we had omega more than 0. In omega less than 0, high T or low T behavior was same. Remember, they had a free energy curve that always sloped downwards. So in this one, we had G, delta G versus composition that always looked like this, irrespective of the temperature. While if omega was positive, then you had a competition between energy and entropy. And in this case, at low T, at high T, it looked similar to what we had for omega negative case. At high temperature, it was similar, right? Because entropy dominates, so you get up this entropy dominated picture. But at low temperature, we got complicated behavior where the delta G curve could show little peaks in the middle, right? So the G versus XP looked like that. So we will get back to this behavior on Thursday. We will get to this on Thursday, and there is a lot of interesting stuff that on Thursday. This is connected to the phenomenon of phase separation. So you basically have two phases separating, but we are not going to worry about that today. Today, we are going to focus on the case when we have full mixing. Anytime you don't get two different clusters forming, anytime you add something, it just mixes completely, okay? So that's the idea. So let's work on that. And with this understanding, so today we are thinking about the case where it's a fully mixable system, which can be modeled using a regular solution using omega less than 0. So I want to emphasize something here. Regular solution is a model. Fully mixable is something else, right? Regular solution is one way to model a fully mixable system. There could be other ways too. So in order to construct this phase diagram, we will go to next page because I need to draw many things. So I will try to write a bit smaller and construct everything. Okay, so what I'm going to do today is to, and we are specifically interested in temperature composition phase diagram, okay? Because we could have had a pressure temperature phase diagram. We are not talking about that. We are talking about a temperature composition phase diagram. So what we would like to plot is, and we will keep adding information here in the top right, we have a box. In this box, the y-axis is temperature, the x-axis is xb, which goes from 0 to 1. And this is how the temperature goes up. And this is how xp goes up. And we want to plot at which point will we have liquid, at which point we will have vapor, will we have coexistence, will we have triple points. We want to see all that kind of behavior. So let's start with a very, very high temperature, which we call T1. Okay. So T is equal to T1, very high. And we are talking about temperature composition phase diagram at constant pressure. So which state function should we look at in order to get spontaneity? Gibbs free energy, right? At constant pressure. So we will look at Gibbs free energy at and so what we want to do effectively is to compare at any temperature the Gibbs free energy of the vapor with Gibbs free energy of the liquid. Okay, that's what we want to do. So at very, very high temperatures, we can make a plot for G versus XP. And we are working in a regular solution model. Okay, so for vapor or for liquid, both of these plots are going to look like what we drew over here, this thing. Okay, they will both look like a curve that just goes down and then comes back sharply at the up. So we will have one curve that looks like this. Let's say this is my G liquid. Here's a question. I have no chocolate, but hope you still answer. Where should G volume be? G vapor be? Above this one, below this one? It should cut it. At very high temperature, which should have lower free energy, liquid or vapor? So, at very high temperature, why should liquid have lower free energy? If I just keep heating you, you will liquefy, but at some point you will vaporize, right? So vapor is more stable. So at very, very high temperature, vapor should have lower free energy. And that curve will also behave the same way as this curve. There will be some qualitative differences, but overall it will be the same thing. So at very high temperature, you will have a vapor curve that is far below the liquid curve. What should happen at the end? What should be the ending value for both of these curves? Should they be the same or different? It is the mixing. It is the, remember, it is not the free energy of the pure phase. So it should be the same. In fact, it should be zero, right? There is no mixing at the end, be it liquid, be it vapor. At the ends, you always have zero. So both go up to zero, right? Because what we are really plotting here is delta mixing G. I will be writing G, but what we really mean is delta mixing G, right? So at pure components, you know, don't have any mixing. So vapor or liquid doesn't matter, it's zero. That's fine. So what does it tell me about the phase that will happen at T1? That's vapor, right? Purely vapor. So at this temperature, we have only purely vapor. Let's go down a little bit. Let's go down to temperature T2 and look at this same set of curves. So again, we are looking at delta So we are looking at delta mixing G versus XB for G liquid and G vapor. So the question now is, relative to the curves you had at T is equal to T1, should either of these curves move up or move lower as you decrease the temperature at constant pressure? Michaela, what do you think? Your hint is dG is equal to VdP minus SdT. So at constant pressure, what is partial G by partial T? Negative entropy. Is that positive or negative? Entropy is always positive. So this is negative. So what does it tell me about G with change? If I increase the temperature, G should go down. And if I decrease the temperature, G should go up, right? We use this idea. We visited this simple relation. And this is really nice because this has nothing to do with ideal behavior or anything, right? This is really, really powerful. So what does this mean? All G curves go up. They move upwards, okay? Which one will move by a higher amount? Liquid or the vapor? Right? The entropy is higher, right? So the rate at which you move is minus S. So entropy for vapor is higher, so that will move. So what this means is that the gap that you had between the liquid and vapor over here, this gap will start to shrink. And it depends on what temperature you have. Let's say temperature T2 is high enough that it looks something like this. So the G liquid is still somewhere over here, but G vapor has really started to catch up. Okay, so one is G liquid, one is G vapor. And this behavior really comes from S vapor being more than S liquid being more than 0. That's the idea over here. Okay, so they both catch up. So at T2, we still have vapor dominating everywhere. Now let's decrease the temperature even further. Let's go to T3. Same behavior, vapor will keep moving up, liquid will keep moving up, but now the vapor catches up. Okay. So we have delta mixing G versus XB. And at this point, something interesting happens. You have the liquid that looks like this. I should have used different colors for liquid and vapor, but that's okay. So, and now, let me do that anyway, for the sake of, also I need to draw this figure bigger because I will be doing some stuff inside it. So let's draw a bigger one. And here we have delta mixing G versus XB. And I will use now dark green to draw the liquid. This is G liquid. And I will use red to draw vapor. Okay. And these curves are a bit tricky to draw. Let's try once again. So, because it's easy to make, yeah, well, this is correct, but it leads to more complicated behavior. I want a curve which intersects only at one point. So the best way to do it is, and it's qualitative. So let's do something like this. Okay, something like this. So keep in mind now that this is G liquid and this is G vapor. So what has happened is that G vapor has moved so much up that it has started intersecting the G liquid. Yeah, go ahead. Oh, it means all sorts of things. We will talk about all that. Yes. Yeah. First, let me see what happens to the composition. Okay, what happens to the, so now imagine you are at this particular composition. Okay, and pay attention. I'm going to zoom in here. Let's say you are at this particular composition. Let's call it some composition X1. Okay. If you were purely liquid at this composition, you would have the free energy GL, right? If you were purely vapor at this composition, you will have, so if you were purely liquid, you would have this free energy GL. If you were purely vapor, you would have this free energy GV. So as per this argument, what should you be at this composition? Liquid. But is that the best you can do? Something very interesting happens here. The system learns that, and let's see if I can draw it carefully. I'm going to draw a straight line which touches both of these curves at exactly one point. Okay. So I have drawn a dashed black line, which is a tangent to the red curve exactly at one point, and which is a tangent to the green curve exactly at one point. Okay. So pay attention now that if you were purely vapor, you would be at the red curve, very high free energy. If you were purely liquid, you will be at the green curve. Looks like there is some loss in free energy. But you could do something else. What if you were to lie along this fictional curve, this straight line, and take this point, which I'm going to draw with a star. The star clearly has lower free energy than the green and the red, right? But what does that mean? There is no phase that corresponds to the free energy of the star. So it is mixable, but it looks different. What happens now is that you have a mixture of two compositions. You have a liquid forming with this composition here, and you have a vapor forming with this composition over here. So it's fully mixable, but inside those two phases. So all of a sudden, you don't have one phase dominated. Your system realizes that if it was to split into two phases, where one phase is which one will have higher XB, liquid or vapor? Someone except Alex and Michaela. Someone who has not answered. Huh? Vapor has higher XB, right? So you have split into a B-rich vapor and a A-rich liquid. It's all relative for this particular value. Even the vapor has more A than B, but relative to each other, right? The vapor has more B than liquid. Oh yeah, good point. So this is B-rich liquid because the green curve was, yeah, absolutely correct. Sorry about that. So that's why you see the colors were important. So actually it's the opposite of what I first said, but hopefully that's clear to. Is that clear? So why is this possible? Why did I draw the common tangent? Not you. Spoken enough, someone else. Sorry. I know you're enjoying this. What is the meaning of the derivative of G with respect to composition? Have you seen this before, Nick? G, this is for Nick. So G is a function of PTN, right? What is partial G by partial N? Chemical potential, right? So XB is nothing but N in a constant composition system, right? So this is chemical potential. So the common tangent tells us the slope of the tangent is telling us what is the chemical potential of B in that phase, right? And if you want two phases to exist in equilibrium, what is the second law of thermodynamics for phases? The chemical potential should be the same, right? So this is very interesting because it means that even if you were at some other green point over here or over here, you would drop down to some other point on the mixture, somewhere over here, but the concentration of B in the vapor that forms and the concentration of B in the liquid that forms is going to be the same. It's only that different amounts will be different, okay? So the common tangent here tells that mu B, the red one gives us the slope of the vapor, right? So mu B vapor, and this one gives us the slope of the liquid, mu B liquid, they are equal. That's why we need to have a common tangent. They cannot split into anything else, right? They cannot split into any other composition. For these two curves that I drew, can you draw any other tangent which satisfies this property? There is only one unique one, right? You could imagine some complicated free energy curve where you have more than one solution. Here, there is only one straight line For these two curves, there is only one straight line, which is a tangent to both of them. Right? Is that clear? There is no other straight line. So this, okay, let's recap this once again. Yeah, go ahead.
So one doubt I have. So at low XP, why is the free energy of liquid greater than the free energy of gas?
Okay, so that's what I was going to recap. We started with a temperature where vapor was always lower than G liquid. Okay, very, very high temperature. Now you increase the temperature. What happens to G vapor?
G vapor increases.
Increases. G liquid also increases. Which one increases faster? G vapor. So they keep increasing. At T2, G vapor is still lower. So this is a fictional setup in which you had two curves and they were going up and one of them just crossed it. That's the idea here.
So how do you know that they cross in that way?
You could draw it in 50 different ways. The physics will remain the same. You will still get some behavior. Okay, maybe they crossed on the right side. Maybe they crossed at 2 points. The physics will remain the same. This basic picture that you have to draw a common tangent, that persists the same, right? So I'm not claiming this is the only way they can cross.
Why can't they simply overlap each other?
They can do whatever you want. They can do whatever you want.
If they overlap, then at every point.
Will they overlap at every possible temperature? Is that possible?
At a particular temperature.
And then you increase your temperature further. Let's go and talk about that one.
Then they will not intersect at all, probably.
Come on, man. You're really pushing the math here. You want to come up with some funky curve where it's all these things happen? Okay, go ahead. I'm not claiming there is no curve, but you're really pushing the extremities here. Most of the time, at very high temperature, G vapor will be completely below G liquid, and at very high temperature, G liquid will be completely below G vapor, right? And this is a typical setup. I could write down mathematical equation. If you really want me to be rigorous, I would use the math for the regular solution and show you this is what happens. But you have to take my word here that this is the typical behavior. What you're describing will be some very peculiar phase diagram where this behavior just becomes like point-like. You're reminding me of Alex at the beginning of the semester. He was very interested in peculiarities like this. And look at him now.
And also, what is the when you draw the common tangent? So, what is the there are many points that do not lie on the two curves. So, how do you physically relate those points? For example, the point x1. You are saying that it belongs to a mixture, but how do you physically relate it?
That's what I said. So at x is equal to x1,
it's a mixture, but
the G of the system is equal to some, let's call this as GA, and let's call, no, GA is a bad name because we have using A for A and B. Let's call this G1 Roman subscript, and let's call this G2 Roman subscript. It is some combination of G1 plus some combination of G2. This is the physical picture. You have split into two phases. Now, if X1 was right in the middle between vapor and liquid, what will be the value of C1 and C2? It will be 0.5, 0.5, right? So in Thursday's class, we will use Liver's rule, something known as Liver rule, to learn how to calculate the value of C1 and C2. But the physical picture here is, and we will talk more about the physical picture in the sense that how this process actually happens. This process happens through something known as nucleation and growth. You have to form a nucleus which becomes bigger and then grows. Okay, we will be talking about that. So physics will come. For right now, look at the math, physics will start coming, you know. So it's after Thursday's class, it will glue in together. Okay, so for now, the thing to keep in mind is if at composition X1, you were all vapor, you would have the free energy GV. If you were all liquid, you will have the free energy GL. You could go to a fictional state almost lying on the straight line connecting these two special points, a very special straight line, which is the common tangent. And Gibbs was the first guy to do this, I think, the common tangent construction. So, and so at this point, the system goes into two separate phases. It goes into a vapor, which is relatively richer in A, and a liquid which is relatively richer in B. This is for this particular intersection of the two curves. You could imagine some other intersection, but the same idea will apply. So let's for example, draw one more on the next page, and then we'll come back to this. So for example, let's just draw something else. So we have something like this. And we have now, what are we using for vapor? Red. We have vapor that exists like this. And for liquid, we are using green. And we have liquid that exists like this, okay? So now the intersection is a bit different, right? The thing is happening on the right side. But the same idea here, that if you are, so the first thing you need to do, once you are faced with two such free energies, okay, the first thing you will do is to, how does this all work in practice? You would do some calorimetry experiment, right? You would get your delta H value. If you would use your delta H value and gives Helmholtz equation to get your delta G value, you get your different curves. So once you are faced with these curves, and this is G, and this is XB, and red is GV, and green is GL. What should be my next step in order to figure out what phases will form at this particular temperature? JP, what do you think? How should I proceed? How should I find a comment? How would you write a code for this?
You find the derivative and find
proceed systematically. I'm asking you to write a pseudocode. Tell me, how will it look like? What would be the first step?
You find the derivative of each.
Correct. So I will pick a phase, right? I will pick the liquid phase, and I will go to this point on the liquid phase. How many tangents can I have here? One, right? I will draw a tangent. I will see, is this curve a tangent to the vapor anywhere? Nope, right? I will move my concentration a little bit, draw a tangent. Is this a tangent to the vapor anywhere? Nope. It will just so happen that there will be one particular point at which, when I draw a tangent, I will suddenly get a click that it is a tangent to the vapor also. It's a very, very special point. Now, imagine if you had the regular solution type free energy where you had a bump in the middle. You can see already how these things will be complicated, right? You could have one common tangent in one part of the free energy, another common tangent in another part of the free energy. And that's a whole different discussion. So you find this common tangent. And what this tells you now is that all of this part to the left over here, the liquid has lower free energy. You are going to be purely liquid. All of this part to the right, the vapor has lower free energy. You are going to be purely vapor. And of course, Kinjal is raring to go and tell me what happens here. You have to do a common tangent over here, right? A separate common tangent in that part. So go ahead.
I find tangents to the same phase, like 2 points.
Yeah, so then you have to start, it gets a bit more complicated. Once you start finding more than one intersection, and I don't want to get into that because it will take a few but it's a basic idea. You get some linear equations and you have to solve it. It's the same idea. There is a whole journal known as Calculation of Phase Diagrams, CalFag, which talks about things like this, So, and here you would have to do another common tangent, right? Because the curves that I drew, but this is a simple phase diagram in which, go ahead.
So I don't understand why at the left of the tangent it will be G2. What do you mean by that?
Which is lower free energy left of the tangent?
The liquid has lower free energy.
So which should exist? Is there any benefit in separating into two phases? You can separate into two phases only of this concentration. That's really the takeaway here. When you have phase separation, you cannot find two phases with arbitrary concentrations. The amount of these two phases will be different, right? You could have 10% liquid, you could have 90% vapor. You could have 50% liquid, you could have 50% vapor. So at this point, when phase separation starts to happen, the red one over here, and you split into two phases, it will be 100% liquid, right? And 0% vapor. But at this blue point, it will be 100% vapor and 0% liquid. In this middle point here, it will be something like 50% liquid and 50% vapor. The point to keep in mind is the concentration of the liquid and the concentration of the vapor will be constant. That's not going to change, correct? In the middle, yeah, there will be some point. And we will talk about the ratio next time when we do Liverpool. So let's get back to this one. So today we are talking about a phase diagram where the curves intersect only at one point, right? If they were intersect at more than one point, then the phase diagram would, as you can see, immediately start looking more complicated. So now let's get back to where we started. So this is T is equal to T3. At T is equal to T3, Kinjal, you tell me which phase is this one? The blue line that I drew over here to the left of this one. Red is lower, right? So that's all vapor. This is vapor plus liquid, and this on the right is liquid, right? So if I go to my thing over here, what am I going to see? I'm going to see that some part of it is vapor. In the middle, we have vapor plus liquid, and then we have liquid. Okay, so suddenly at this temperature, we are seeing three different things, depending on what composition you have. And again, if I was to use, let me mark this for later, example of more complicated construction, then I would have to do two common tangent lines and try to worry about it. Later, it leads to, your question, Alex, actually goes to something as convex hull, and you have to solve it as an optimization problem. And it keeps getting more and more complicated to do that. So T is equal to T3, this happens. Let's imagine an extremely low temperature. T is equal to T5. At T, and then we will come back to an intermediate temperature, T is equal to T4, okay? So at T is equal to T5, if we make the temperature very, very, very low, which curve will be higher? Swimming. At extremely low temperatures, at very, very high temperatures, vapor was lower than liquid. At very, very low temperatures, which curve will be lower? Huh? No, so as I increase the temperature, as I decrease the temperature, think intuitively. Higher. Why? Think through this relation. Right? It's entropy dominated. So as you decrease the temperature, the curves start to go up. And different curves move up at different rates, right? So by that argument, this will completely flip. G vapor will be completely above G liquid. That is the idea. Oh, and also intuitively, we know that at absolute zero, G solid is the most stable, right? Solid is always the most stable. Follow above, G liquid is above that, and G vapor is above that. At very, very low temperature, everything should be one perfect solid. So at extremely low temperatures, we are going to have G vapor that is like this, and G liquid that is like this, okay? At extremely low temperatures. Of course, if we go even lower, then we should have solid in our phase diagram, but you get the idea here. So at T is equal to T5, we are again going to have all liquid, okay? Now let's think about some, the final temperature I want to consider here is T is equal to T4, something in between T3 and T5, okay? So what happens there is that this green curve continues to move up, right? As we go from T3 to T4, the green curve moves up. The red curve also moves up. The green curve moves more than the red curve, right? So for this scenario that I drew over here, it will look something like, qualitatively something like this. The red curve will be here. And the green curve, which has now moved up, will intersect it somewhere to the right. So this intersection point kind of moves to the right. Okay, if you think through it, you will see what I mean here. So these two common tangent points, if I use JP's algorithm now and start drawing common tangents, I will find that the points at which I got that common tangent, both of them have now moved to the right. Okay, so you have a bigger vapor phase. You again have some vapor plus liquid, and you have a liquid one. Okay, so at this temperature, it looks something like this: vapor, vapor, vapor plus liquid, liquid. Go ahead. Mhm.
Does it mean that if I have some kind of low alcohol mixture and I want to get strong alcohol, I cannot do it with only one distillation cycle?
No, you have to repeat. That's the whole idea. So this is what leads to in PChem, you must have studied this at some point, right? You have to do repeated distillation. You have to distill. He's very interested.
Now
in
you
this.
have my attention.
I've been told you have conversations with Sukhadev on vodka. No, you have to just keep removing it. You cannot, you will keep, every time you get your alcohol vodka, it will be at the same concentration. When you come back, you cannot, yeah. So let's complete the phase diagram before we get distracted by the application question. So we have, you can join a boundary over here, and it's going to look something like this. It's like a lens. Everything above the top of this curve is vapor. Everything below this curve is liquid, and everything in the middle is vapor plus liquid. Okay. You could have a lens which was facing the opposite direction. Depending on how the curves moved, you could have more complicated things. But this is the simplest phase diagram in temperature composition space that you can have for two things that mix fully. Yet you have two competing phases. Okay, so let me draw this phase diagram again on next page. On next page. So we have temperature, we have composition. We knew that a better way of thinking about it is to let's think about this in terms of grids. Okay, let me draw grids over here. And this is as temperature goes up, and this is XB goes from 0 to 1. So at very, very high temperature, we look at a particular row. Everything is going to be vapor, right? It's very high temperature. GV is lower than GL. At very, very low temperature, everything is going to be liquid. As you decrease the temperature, you start seeing some vapor plus liquid. The region which you have vapor plus liquid, that comes from the common tangent construction, right? Again, back to liquid over here. As you decrease the temperature, we showed that, and I'm being a bit qualitative over here because you can be as quantitative as you want. It could be a few lines of code in Python or MATLAB, and you can plot the whole thing by assuming the regular solution, right? It's quite easy. So now this thing will start to extend or move to the right. And then you have something like this: vapor, vapor, vapor plus liquid, vapor plus liquid, vapor plus liquid, 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 vapor, 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 vapor plus liquid, vapor plus liquid, vapor plus liquid, liquid. No, I did something very wrong. Does anyone see what did I do wrong?
Second row.
In second row, not Alex, someone who has not answered. Patrick, what terrible, terrible, horrible mistake did I make in this second from top row?
It should be all vapor to the right.
Exactly, given my phase diagram, right? So we could have a system where it looks like this, but for the thing we drew, this is not, well, it can't happen ever, right? Because it will be opposite of what we said, sorry. So sorry for that. Thank you, Patrick, for catching my mistake. Yeah, then it will be, then you could have some setup where you could, but we are not doing that, right? So yeah, for this particular case, this is not correct. So this would be liquid, this would be vapor plus liquid, then vapor, 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 okay? Liquid, vapor plus liquid, vapor plus liquid, vapor, 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 vapor. Arman is very happy, he has done this in his undergrad, right? In the course of 684 and 687, it's actually quite democratic. If you think he has an unfair advantage because he has done phase diagrams, in 687 there will be many things which some other people here would have done it in the class. You took Millard-Alexander's 481, right? So when I get to Bose-Einstein and Fermi-Dirac, you will have a blast because you can relate to that using quantum statistics. So it's fairly democratic. While the people who haven't done quantum mechanics at that point will be like, what the fuck's going on? I have no idea. Yeah, go ahead.
Shouldn't in row 4, the second column be already liquid?
Yeah, it's a grid, right? You're right. I can make it already liquid. That's correct. But the point is that overall it's moving to the right, and I have to change that too, right? So I'm gonna stick with this. Let's do that over here. Let's make this over here liquid, 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 vapor plus liquid, vapor plus liquid, vapor, vapor, liquid, liquid, liquid. And then all liquid. So now I can draw a locus joining the whole vapor plus liquid part. Let's make this also vapor plus liquid, or my life will be a bit complicated. The qualitative idea is the same. That's going to look something like this. Okay, that's the idea. That's how you get this lens-shaped curve. And a lot of chemicals follow this. For simple chemicals, this tends to be the behavior. For complicated chemicals, of course, you get all sorts of funky different behavior. So everything in the middle is a two-phase region of liquid plus vapor coexisting. Everything to the left is liquid, everything to the right is vapor. And so that was the idea. I'm going to draw this once again and then discuss something about it, but I won't draw it on the grid. There is a reason why, especially in statistical mechanics, you have to use ideas from different places when you take it next semester. And I think many of you will be there because it happened later, right? It happened after quantum, at the same time as quantum mechanics. It happened in order to explain things. So it's really, in a sense, application driven. I will be talking about black body radiation next semester because in a sense, nothing to do with chemistry. But if you think about it, it has a lot to do with chemistry because if you think about light matter interaction, which people study in chemistry, that's the type of stuff. So next semester, there will be always pockets where you will feel a bit like, I don't think I know what's going on here because it borrows on something else. And I will try to help you with background reading in that. So this is temperature, this is XB, and we drew a phase diagram that looks like this. All of this is liquid, all of this is vapor, all of this is liquid plus, what did I do? All of this is vapor. Let's imagine there is a competing solid in the whole thing. What could that be? You could imagine a very simple phase diagram that actually looks something like this. Right? It's totally possible. If anyone can find me a real system, chemical system, which has a phase diagram that looks like this, I will give you a prize. I don't know what the prize will be. And the curves could be opposite or something, I don't know. And for some systems, this lens could actually be symmetric. It could look like this. It's possible, right? But go and think about it if you can dig up a phase diagram that looks like what I drew over here. The prize might be extra homework problem. It's your opportunity to learn more. Yeah, go ahead.
Can you back up one slide,
Yeah.
please? So just so I understand what's going on, each horizontal slice
Mhm.
of the grid corresponds to how you marked out the regions on the.
Yeah. Using the common tangent construction.
Okay.
So exactly. So this is what I'm coming to over here. Let's think about this point over here, this blue point. This is a point in which you want to split into a liquid and a vapor. This is also a point at which you want to split into a liquid and a vapor, right? This green one is also a point at which you want to split into a liquid and a vapor. All of these are at some common temperature. The thing to keep in mind is, irrespective of whether you are at green, blue, or red, the concentration of the liquid that you form will be here, and the concentration of the vapor that you form will be here. Okay, it's just that relative ratio will change. Is that clear? Any questions about this?
So can you go over this concentration thing again? Relative, what do you mean by relative ratio?
Yeah, we are going to talk about that a lot now. So just hold on for a moment, okay? So what do I mean by relative ratio? By relative ratio, I mean something known as Liver's rule. Let me talk about that. So let's go back to this phase diagram that we drew. Not a parabola, sorry. Okay, so we have temperature and we have composition, and I drew something that looks like this. So this is all vapor, this is all liquid, and in the middle, you have liquid plus vapor. This is xb is equal to 0. This is xp is equal to 1. So I will get your question exactly in a moment, Kinjal, because that's all we are going to talk about right now. So it will become clear. But before that, I want to see how much intuition you have for this. Tell me, Nathan, as we go from xp is equal to 0 to, let's say, xb is equal to 0.25, what happens to the boiling point of the liquid? What happens to the temperature at which the first vapor appears, at which the liquid starts to boil? Does it go up or does it go down?
It goes down.
How can you see that? From the slope of this curve, right? It's downward facing.
Right.
So at any composition, at this composition, this is the temperature at which the first vapor starts to appear, right? That's boiling, the first coexistence. As you keep heating the system and you get to this temperature, you get a particular, that's the first time you see vapor. So in this sense, you can see almost it's like a boiling point suppression, right? As you are mixing things, the boiling point is going lower and lower and lower and lower to the right. But if we had a phase diagram where this lens was faced the opposite direction, the other thing would be true, right? So, but you can read the boiling point out of this. So going back to what Kinjal was asking, let's talk about that in detail. So I want you to focus on, let me write this liquid up here so it does not interfere with us. I want you to focus on a particular point O. Okay, I will call it point O. Well, actually, we can keep it above our xb is equal to 0.25 line. It's just that we are not talking about specifically 0.25. We are talking about some concentration. xb is equal to some value. Okay. Some value. I don't know what that value is. Some particular value. And at this point O, we know it's going to be a mixture of liquid and vapor, right? Because it is in the two-phase region. So my question for you is, first question, At point O, we are going to form a liquid and we are going to form a vapor. What will be the concentration of the liquid that we form? Kinjal. Given this phase diagram, if I asked you, so Kinjal, do you agree that at point O, we have a two-phase region? We are in liquid and vapor, right? So what is the concentration of the liquid that forms? How did we get this boundary? We got this boundary through the common tangent rule, right? So the concentration of the liquid is this point where you touch this line, the curve corresponding to the liquid. The concentration of the vapor is this point where you touch the vapor line. And I think it has some Latin name. The liquid one, the bottom one is known as liquidus. The vapor one, I don't know. Vaporous, vaporub, I don't know. Vaporub is like a particular ointment they sell in India for headache and things like that. I don't know what you mean. Vaporous, liquid curve and vapor curve. Let's just call it that. Okay. So this is the concentration. Let me draw a straight line of the liquid that forms. And this is the concentration of the vapor that forms. Let's give both of them names or value. Let's call this particular concentration as X1 and this particular concentration at X2. So at point O, system exists as a liquid with XB equal to X1 and vapor with XB equal to X2. My question for you is, so we all agree that it will exist as a liquid and as a vapor. And there was nothing special about point O, right? Point O could be lying over here. Point O could be lying over here, the black dots that I drew. Irrespective of where your point O is, the concentration of the liquid will always be X1. The concentration of the vapor will always be X2, okay? So Alex's plan of getting very, very pure alcohol is not going to work. You're limited in the concentration of alcohol that you can get. It's derived by the phase diagram.
Or I can boil very, very slowly with very low temperature.
Yeah, so you can play with the temperature, and the other trick you can do is to play with the kinetics. And that's another story. In this class, we don't talk about kinetics. But my question now is, so, okay, we agree that the liquid will always have concentration XB is equal to X1 and the vapor will always have XP is equal to X2. There is one thing we did not talk about, is how much of it will be liquid and how much of it will be vapor. That's different from the concentration, right? So if the point O was over here, at the very left end of this line, the liquid will still have concentration X1. The vapor will still have concentration X2. But how much vapor will we have? 0, right? Does everyone agree with it? Aiden, do you agree with that?
Still thinking.
At this point, how much vapor do you have? Over here?
Is 0.
So this point is basically an extension of that. This is like a very entered the two-phase region. So you might have some vapor, but it's mostly going to be all liquid. The opposite happens at the red point over here, right? This is going to be all vapor. You have no liquid. So somewhere in the middle, you expect to be 50% liquid, 50% vapor. So the question now is there a way to calculate? If I gave you a phase diagram and I gave you the location of O and I asked you how many moles? So the question is, at point O, the number of moles of A in vapor is equal to how much? And number of moles of B in vapor is equal to how much? I will work with number of moles and then come back to mole fraction. Okay. Similarly, number of moles of liquid is equal to how much? And number of moles of B in liquid is equal to how much? We want to figure out these 4 quantities. Okay. And before I forget, this particular line that connects the one end of the phase diagram to the other end of the phase diagram has a special name. It is known as the tie line. Okay. So this is the problem we want to solve. More precisely, we are interested in NA, which is the number of moles of A in vapor plus number of moles of A in liquid. And we are interested in NB, which is number of moles of B in vapor plus number of moles of B in liquid. And we want to find out the value of NA and NB at, no, that we already know, that is the mole fraction, so we don't want to do anything with that. So, and we can also talk about NL. I'm just not adding any new information. What will NL be? Where will NL come from? It can come from A, it can come from B, right? So NL will be NAL plus NBL, and NV will be NAV plus NBV, okay? So what we want to do is to come up with a way of calculating these two things, NL and NV. How much liquid is there and how much vapor is there? Why is this sufficient? Because if we figured out how much liquid is there, we already know the composition of the liquid, right? We already know that the composition of the liquid can be read from this tie line where it intersects. So we can immediately go and tell you how much of the liquid is A and how much of the liquid is B, right? We already know that. That answer is already done. What we want to figure out is how much of the system is liquid, how much of the system is vapor. We know at this end, on the liquid end, it's going to be entirely liquid. At the vapor end, it's going to be entirely vapor. Okay, so that's what we want to understand. And I will not do it fully this time because we already have lots of new information today, but I will stop a bit early today. The pace was good. I'll give you your midterms, etc. So let me draw this and I will state the result. And next time we will prove this. However, I would like you to go home and try to prove it yourself. It's not hard. Try to do it yourself. Then the next class will be a slam dunk. I really want everyone to try. So the problem we are trying is, I'm drawing the same, not the parabola. I'm drawing the same phase diagram in which I have temperature, composition, we have liquid, we have vapor, and we have a combination of liquid and vapor, and we have a particular point O, okay? At this point O, we can draw common tangents and we can read out the composition of the liquid that will form. That will be X1, okay? And we can read out the composition of the vapor that will form. That will be X2. But the question is, at O, what will be the number of moles of liquid and what will be the number of moles of vapor, okay? So Lever rule answers this question. Levers, is it levers or lever? I don't know. It's Lever rule. Lever was not a person. Yeah, I should have known that. It's Lever rule. Lever rule says something interesting. It says, go and measure this length, okay? The length from the nearest liquid point and call it L vapor. Length vapor, okay, LV. And then go and measure this length, which is the length from the nearest liquid point, call it LL, okay? So what is the value of LL at the green star that I drew? 0. The distance from the nearest liquid point is 0. So Lever rule says that if you measure these two lengths, then NL multiplied by LL is equal to NV multiplied by LV. Does this make sense? At point X, or I don't know, let's call it point K. At point K, which is this one over here, what is the value of LV? What is the distance from the nearest vapor line? 0, right? LV is equal to 0. So what does that tell me about NL using Lever's equation? 0, right? If I put LV is equal to 0 over here, then NL must be 0. NL is equal to 0. Does that make sense? That's what Aiden told us, right? We are on the other side of the curve. It's almost all vapor now. So it makes sense at the two extremities. So this is, and you can use this to convert into mole fraction. What you can do is to divide, and I'm not proving it. I will prove it next time. You should try to do it on your own. And more important than the proof is that you should remember this relation, because you will encounter phase diagram irrespective of what type of chemistry you do. And this rule works for everything. We won't assume ideal gas. We won't assume anything. It could be RNA. Michaela is working on cytoskeletons and things like that, right? It could be something very complicated. As long as it is in equilibrium, it will apply. Unfortunately for Michaela, it might not apply because cytoskeleton is often not in equilibrium, right? It's a driven system. So if you're out of equilibrium, you're kind of screwed. Phase diagram becomes complicated, right? But if you're in equilibrium and a lot of life is in equilibrium, or some sort of equilibrium, then it applies. So in order to get to mole fractions, let's divide both sides by NL plus NV. So what do we get? So we have NL divided by NL plus NV is equal to LL. So I want to mention that we will prove this next class. And this is Lever rule. So if you divide both sides, then NV divided by NL plus NV, LV. So this is the mole fraction of liquid, right? So XL multiplied by LL is equal to XV multiplied by LV. Also, XL plus XV must be equal to 1. If you're talking about mole fractions and there are only two phases, you are going to be either liquid or vapor, right? Therefore, 1 minus XV multiplied by LL is equal to XV LV, or LL minus XV LL is equal to XV LV. Therefore, XV is equal to LL by LL plus LV. There's a lot of L's. The small l indicates length, the capital L indicates liquid. So perhaps 10 years ago in graduate thermodynamics at University of Maryland in chemistry, one would have ignored these topics and be like, oh, you know enough phase diagrams, it doesn't matter that much, it's okay. For biophysics students, for example, people would be like, it doesn't matter. But in the last 10 years, turns out these things are super important, even for out of equilibrium systems. In the body, you can go and look up the phenomenon of liquid-liquid phase separation, which is really, if you understand what we are doing today and in the next two classes, then that whole literature of liquid-liquid phase separations in RNA opens up for you. So it turns out these things are really fundamental, because even though life is out of equilibrium, we are not in a ds is equal to 0 state, right? Our entropy is increasing, we know it as a whole. But it's a question of observation time, right? If you look at a small enough, if I'm getting philosophical here, but you see my point. Equilibrium principles can still be used to understand biology. So we haven't talked about phase separation yet. We saw it, we saw a glimpse of it as to how we get into two different phases. But next time we will, once we have done Lever rule, we will prove this. So let me summarize what we are going to do next time, which is, so next class, we will prove Lever rule. And I really want you to go and try proving this. Make an honest effort, okay? Don't look up internet or anything. Just try to think, how would you prove this? You can do it on the basis of information I've given here. Really try to do it. It will be good for your understanding. We will prove Lever rule and study phase separation. something else known as miscibility gap, and something known as spinodal decomposition. And we will contrast. This spinodal decomposition is very, very interesting. It's a barrier-less process. It's like a fractal in which all of a sudden phases form at all possible length scales. And this will take us 2 classes. Then we will finish our discussion of phase diagram. And after this, we will talk just maybe 1 class or 2 class, a little bit about chemical equilibrium. And I want to remind you of the concept of activity, which you have probably seen in your undergrad PChem and have definitely forgotten by now. I'll tell you a little bit about activity, which is like the brother of fugacity for chemical equilibrium, okay? So we'll talk about this. And then there will be 1 homework. It will be a small homework. It will not be a very long homework where you can cover some of the concepts. I will probably give it out Tuesday. There will be 7-day turnaround time. Okay. The moment you have all been waiting for. What is this? This is homework. Okay, this is homework. It's in alphabetical order. I can just give it out. It might be quicker. Omar is not here. Jared is not here. Alex is here. Alex, you can come and take it. You used to do that in school. Like here, your midterm too. No problem, right? Ethan is not here. Michaela. One. Arman. Okay. And then Sunil. JP. If I give JP to Sunil, by any chance, let's see. I have your other graded book. Maybe it will show up to you, okay? Oh, here it is. Nick. Where is your other one? Jared, who's next? Nathan? Vanessa? Pinjal? You have brought all the Oraya? Yeah. And I want to talk about 1 problem after this, which is the natural variance problem. Aiden? And the homework and solution keys for both are already posted. Vedant is not here. Is that Vedant? Sophia is not here. Why do I have only 1? Did you submit only 1?
You got another
Oh,
from
okay. You got it. Okay, I want to talk about only 1 problem, which is the natural variable problem. Not all thermodynamic functions have natural variables. The whole idea, where did we get to natural variables from? The idea was we talk about S of NVE, that is our ground truth in this class, right? Everything starts from there. S of NVE is thermodynamically complete. It knows everything you want to know. And when you Legendre transform into some other function, information is not lost. This is like doing Fourier transform, right? You can look at a function in real space and you can look at it Fourier transform. They carry the same information. There is no change of information. You can Fourier, you can invert, right? Fourier transform is not like, a Legendre transform is not like Google Translate, where you translate it once and you translate it back and it tells you something else. It's always going to be the same. So once you have S of NVE, if you can Legendre transform it into something else, then you have a thermodynamically complete representation. And the differentials in this representation are your natural variables. Does this mean that energy cannot have natural variables? Energy actually might, because we also had the monotonicity relation. Pressure definitely cannot. Why? because it's intensive. You're already losing information about number, right? And remember, Lagrange transform did not allow us to go from extensive to intensive. We tried to go from extensive to intensive when we got to 0. So that's why we cannot have natural variables for everything. We can have natural variables for thermodynamic quantities that are complete, okay, that carry all the information. The idea being that if I told you the pressure of a system, I have no information about your temperature, right? It could be doing whatever you have. If I could do S as a function of NVE, then I know everything. Pressure as a function of whatever will never tell you about mole fractions. That information is lost, right? You don't have information about chemical equilibrium. That's the idea.